Hello, everyone. Welcome to the final part of Intro to Data Structures and Algorithms in Python. Super excited to be here. Super excited to see everyone coming from Global Hack Week. I hope that you've had a good rest of your Global Hack Week. I know that I've enjoyed my time talking about data structures and algorithms, working with in Python with y'all, even though we were off to a little bit of a rocky start in the beginning. Also, before we get started, I want to drop this in the chat to make sure that everyone is able to get signed in. If you haven't gotten signed in already, please make sure to hit this link to register your attendance with Major League Hacking. It makes you eligible for potential swag, potential achievements for attending a certain number of streams in a week. So make sure to register your attendance for this event. So welcome to the last part of Intro to Data Structures and Algorithms in Python. If you are new to Global Hack Week or new to this stream, I'm going to kind of breeze through a few brief introductions, a little bit of housekeeping, just to make sure that no one's totally confused, but I also don't want to dwell on this all that much, just for our repeat watchers who are here for parts 1 and 2. So if you're curious what data structure or DSA in Python means, it stands for Data Structures and Algorithms. And if you are unfamiliar with what data structures or what an algorithm is, I'll do a quick run through of those as well. So a data structure is a defined way to organize, store, and manipulate data in the memory of a program. And an algorithm is a step-by-step programmatic rule for solving a problem. These are valuable skills, both for landing a job, but also for becoming an efficient engineer once you actually land that job. So that's what we'll be covering today. We went through a few different types of data structures earlier in the course, as well as a few different types of algorithms. But the majority of these streams are focused on actually problem solving and working through those problems together. And as far as who I am, my name is Gabriella. I'm a coach here at Major League Hacking, also known as MLH. If you see that abbreviation anywhere, MLH stands for Major League Hacking, not Major League Hockey. And additionally, outside of my work with Major League Hacking, I'm also a full-time software engineer. And also, as kind of like a brief shout out, the bit.ly link on the screen is the short link for the check-in URL. And then the short link on the right-hand side of the screen is a short link to our slides, but I'll have those shouted out at the end of the stream as well. So no need to hurriedly write that down, just so you know what those links are. And I'll shout them out as we go along throughout the course of today's stream. And as always, if y'all have any questions, feel free to drop them in the chat. But now I have some questions for you. I'm curious, how many of y'all know Python, how experienced you are with it? The options are yes, no, I don't know Python, or a secret third thing, which is you know Python a little bit. And then I'm also curious to know if you have leak coded or taken any HackerRank assessments before. And kind of as a brief explanation for those of you who are unfamiliar with what those are, leak codes are data structure and algorithm practice problems. You can do them on your own. They're typically done in individual rounds, and then hacker ranks are typically assessments. There's a group of data structures and algorithms problems that you will typically do for a university course that's focusing on these types of problems, or in the initial stages of technical interviewing for an engineering position. So please drop that in the chat. This is Beginners Week, so this is a Beginners Week geared stream, but I just want to get a general understanding of how experienced y'all are, so I know how to tailor my explanation, and if I need to dive a little bit more into the actual data structures and Python syntax when I'm talking through the solutions. Also, I'm a little bit sick. I think I'm coming down with a cold or something. So if voice is a little bit off or softer than usual, that's an explanation of why. Drinking plenty of water in preparation for today's stream. But if you're not able to hear me, let me know in the chat. I want to make sure that y'all are able to learn as much and are understanding everything clearly. All right, looks like we have a little bit of a mix. Some people who haven't done LeetCode or HackerRank and are unfamiliar with Python, and some others that are familiar with both. So that leaves us in kind of a middle ground. I know it's a little bit of a odd time, and we're at the end of Global Hack Week. But for the rest of y'all, just pop your answers in the chat or questions in the chat as they come up. Kind of as a brief overview for those of you who weren't here last time and want a little bit of guidance or base level of what we did the last two times. For the first time, for the first part of the stream, we went through strings, arrays, dictionaries as data structures, and I talked through what makes up those data structures, what makes them unique. And we also went through some practice problems before we ran into technical difficulties, which cut our time short. And then in part 2, we made up for lost time, and we revisited some strings, arrays as data structures, dived into dictionaries a little bit, as well as a little bit of set work as well. And then we went over the 2-pointer and sliding window algorithms. We did not get to binary search last time. We'll be talking about binary search this time, and we went through many practice problems last time. So that's kind of an overview of what we did last time. I have all of those in the slides that you'll all be able to check out after the stream is over. All right. So on to what we're going to be doing today. So we'll be talking about the linked list data structure as new material. We'll also be reviewing 2-pointers as an algorithm. And then as far as what's new for today's session, we'll be talking about binary search as an algorithm, as well as time and space complexity, and we'll be mostly focusing on practice problems. The majority of this is practice problems. I talk through how to do data structures and algorithms problems, and I give a kind of step-by-step of how to actually problem solve. We talk through everything together. If you have any questions, feel free to drop them in the chat. But that's kind of overall housekeeping for today. So here are our practice problems. I think, going to do this slightly out of order from what my slides have. So we have our best time to buy and sell stock, as well as 2-sum with a 2-pointer solution. I think I'm going to start with 2-sum in the 2-pointer solution, and then we'll go to best time to buy and sell stock as our next problem. If you weren't here for our last session in this stream series, we have solved 2-sum already, but we haven't solved it with a 2-pointer solution. So this is just kind of taking a familiar problem to us and solving it with a new algorithm. All right. So I'm going to, okay. So I'm logged in, so it has all of the material that we went through last time. If you were here for parts 1 and 2, then you'll know that how I solve these LeetCode problems is that I give a list of what we're given, like the input information in our problem / function, and then I write out what we actually need to do, just so we have a quick understanding of what the problem is actually asking. And then I'll go through and type out what we're actually going to be doing when we code. Sometimes it's like a little bit of pseudocode. Sometimes it's just like English talking through everything to like give myself a sanity check. And then also sometimes hackers like y'all will check me like, that doesn't make sense, or what if we did it this way? It's meant to be a collaborative learning process. I am guiding y'all through this, but if you see anything that doesn't make sense, feel free to point that out, because you're kind of like my, I think it was in the last session, one of y'all had said that you were a rubber duck made out of like Swiss cheese or something like that. So y'all are somewhat my rubber ducks in this problem solving process. So kind of as a quick review / recap for people who weren't here for the last session, I'm just going to talk through our previous solution before we move on to our 2-pointer solution as kind of a refresher, and to get ourselves into the problem solving mindset. Okay, so given an array of integers nums and an integer target, return the indices of two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. So what I said was we're given a nums list and a target integer, and what we actually need to do in this problem is find the two ints in the number, or in the nums that equal target, and return the indices of those integers. So what I said for the steps for the first pass around, we need to create a dictionary to hold these key value pairs. So it'll be the current integer and the index of that current integer. So here we can see in our first example, we have the current integer as well as the index. We need to loop through the entirety of the nums list. And then if target subtracted by our current integer is in the dictionary, then we need to just return the indices because we found two that add up to target. But if we find that our target subtracted by current integer is not in our dictionary, that means that we don't have a previously existing integer in the list that we know the indices of. So we need to add that into our dictionary. And then we know that for every single input, there is one solution. So we didn't have to solve for any edge cases. As you can see here, I solved it like that. So we created our dictionary to hold all the indices. We looped through our nums list. If you're new to coding or unfamiliar with Python, the way this varies from just a normal for loop is that this is unpacking both the index and the actual item in our list. So this will enumerate our list. So we're able to pull out both the indices as well as the actual item. And this is helpful in this case because we are returning the indices rather than the actual item. So this allows us to have both, and we don't need to, it makes the syntax a little bit more simplistic here. So we calculated our difference, which is what we're looking for right here. We checked for it, returned it. Otherwise, we are adding that particular item or that particular integer and the indices. So yeah, and it worked last time. So you can see on LeetCode, all your submissions. That was on the 11th. That was our stream, and we had really good run in memory time, which I'll talk about run in memory time pretty briefly after this. But now we have gone over our first attempt at this. We're going to talk about a potential two-pointer solution to this. So for those of you who are unfamiliar, weren't here for the last stream, we talked about two pointers as an algorithm. And two pointers is essentially when you have a list like this. I'm going to just paste it in so I can kind of verbally talk through it and have that visual element as well. As I'm chatting, I don't know what everyone's learning styles are, so I want to make sure that makes sense. This makes more sense to me when I have something to talk off of and can point at. Okay, so in a two-pointer solution, you'll have a list, and then you'll have two pointers, as is mentioned in the title of the algorithm. Typically, it's going to be a start pointer and an end pointer. Some other ones have weird, weird positioning, but that's the vast majority of them. It'll be a left pointer and a right pointer. And the left pointer will be at the beginning, so it'll be at 2. And then the right pointer is going to be at the end, so it'll be at 15. But we don't actually explicitly set these pointers to both of these actual items. We're setting them equal to an indices, so we can iterate through the list at a quicker pace than a normal for loop. So I'm going to set, in this case, the integer equal to 0, and the right pointer equal to the last indices in the list. Sorry, messing up the verbiage a little bit. And then in the two pointers algorithm, what we do is we're essentially checking for a solution while the left pointer is less than the right pointer. And based on those conditions, we'll either increment the left pointer up. So in this case, if we're incrementing the left pointer up, we would set the left pointer equal to indices of 1, which will make it checking for 7, and we'll keep the right pointer right here. But if our condition is different, then we'll decrement the right pointer down, bring it from 15 down to 11, while keeping the left pointer at indices 0. Yeah. So in this case, what I think will be helpful for a 2-pointer solution is to similarly have a dictionary. Let me talk this through with myself. Because we want to compare these two. Actually, no. Okay, so this is going to be similar to our two-sum if okay. Thinking this one through. So create our pointers while left is less than right. We need to calculate sum of nums at lefts, nums at right. And then if nums, the sum is greater than left, we're going to, or if the sum is greater than the target, then we'll likely want to decrement down. And then if it is if the sum is larger than the target, then I said that the opposite way. If the sum is larger than our target, then we're likely going to want to decrement down. And if it is smaller than our target, we're going to want to increment up. In the previous session, we did a somewhat similar problem where they were sorted with this 2-pointer solution. But I'm curious to see how this is going to work when we don't have them sorted. So we're going to talk through this and see how this varies and if we do need to sort it or if we would need to add a dictionary. I'm just kind of spitballing here with what I'm initially thinking, and then we can kind of slowly work through these. Okay, so well, sum of, okay, if sum is greater than our target, decrement right down. If sum is target, we're going to increment left up. And then the last scenario is that we'll find that sum is equal to target, and that we're just going to return our indices. This is going to be, I'm just curious. Okay. Yeah, I guess that's okay. I'm just going to give this a go before I overthink it too much. All right, and let's see how this shakes out. Oh, oops. Okay. So it's passing 1/3 of our test cases. I think that in this case, we maybe need to have I think we need to set these to be equal, just because in some cases we have two. This is passing in this particular instance. Um, I'm actually I need to talk about case two, because if we essentially need to have them be left is less than or equal to right. No, that wouldn't be the case either because we can't use the same integer twice. I'm gonna submit this to see how many of the overall test cases is passing, but I'm thinking we might need to actually just sort this to use a 2-pointer approach. I was curious to see if there was another 2-pointer approach without it being sorted, but I do think it needs to be sorted just because I think that in order for this logic to work, we need to have the numbers be in increasing order instead of in random order, because we could pass up a potential solution if we don't have them in increasing order. Okay, so in that case, I'm just going to have sort out nums. I can't remember if it assigns it or assigns it to itself. That's not the case. Okay, so nums would be equal to nums.sort. I'm not going to get LeetCode Premium. Okay. Is it one indexed? No. Oh, I see. This is because we've sorted it, so there's new indices, and it's returning the new indices. I'm curious then. For we might have done the only two sum that is possible with 2-pointers earlier. That's my bad. Okay. I think that's the case because these test cases are all under the assumption that they're the initial order, and because we have to sort them for the 2-pointer solution to work, it's not going to work with this particular case. I'll pull up the last one we did just to show y'all what that looks like. Yeah. My apologies for I was trying to do a second run for this problem, but I don't think this is possible with like a normal time and space complexity. Okay, so I have this hidden for right now just because these are the practice problems from last session. But I'll briefly go over what it looks like. So it's a very similar solution to what we actually had over here. But because the test case is are actually looking for the index of the integers that have been sorted, and our if statements are more conducive to a two-pointer algorithm, it will actually give us the correct or passing test cases. But it's the same solution, as you can see. The only difference is that all of the input numbers in the list are in increasing order. So my apologies, y'all. But as you can see, you can't apply every algorithm to every problem. And with it being like a normal time complexity, we could, in theory, solve the normal two-sum with a two-pointer solution. It would just, it looks like Benny said this as well. You can store like the integers or the like the initial indices elsewhere, but it is not going to be a very good time complexity, and it'll be like not very efficient code for what the problem's actually asking for. So that was a little bit of a warm up, maybe unsuccessful warm up, but warm up nonetheless. Gets everyone thinking. Yes. Okay. So that was our first run. We can move on to our next problem. So the next one is going to be the best time to buy and sell stock. I'll refresh this. We don't have my code from last time that I saw this problem, and I'll talk through this particular problem. So you're given an array of prices, and all the prices for this we can assume to just be stock, as is mentioned in this title, where the prices at an index is the price of given stock on that day. So on the first day, it will be, let's see, the first day is technically index 1, so it'll be 1. We can call day 0 maybe the day like it started on the stock market or something, with 0 indices or 0 indexed list. It can be a little funny when you have that as a day. But where you're given an array of prices where prices at an indices, the price of stock on that day, you want to maximize your profit by choosing a single day to buy one stock and choosing a different day in the future to sell that stock. So like the basic philosophy of the stock market is you want to buy low, sell high. And what we want to do in this particular problem is return the maximum profit we can achieve from this transaction. And if you can't achieve any profit, we'll just return a 0 in that case. Give me just a second. I'm going to blow my nose really quick. Like I said earlier, I have a little bit of a cold. Okay, so for this problem, what we're given is a list of stock prices and the date of that price. And then what we need to do to maximize our profit by choosing the day to buy and a different day to sell. So find the most profitable day to buy and a different day to sell. Okay. Edge case. If you cannot profit we need to return a 0. So for this one, what we're going to do is essentially do like a more complex 2-pointers problem. But in this case, it'll be a little bit more complex because we want to calculate the profit between our left and right pointer, if that makes sense. So I'm going to start writing out our steps for this. Okay. So step 1, we need to create our 2 pointers. And then step 2, we'll have our while statement. While left is less than right. And then inside of our while statement, I'll just have this be little bullet points after the numbers, so you're able to see kind of what's actually inside of our while statement. Inside of our while statement, we want to be calculating our profit. So profit will be equal to left minus right. And then we want to also be storing somewhere, we want to have like a variable for our maximum profit. So as we go through the entirety of our list here, we want to make sure that we're not just returning the most recent profit because we want to find the most profitable day. And in this case, we can see that the most profitable day to buy would be to buy on day 2 and to sell on, I don't know what day this is, but to sell on the day that it's 6. We don't want to continue iterating through this and have it be like, oh, we buy on day 2 and we sell on the last day because that's the last version it's checking for and for it to return that. So we need to have something to store our maximum profit. So variable to check max profit each iteration of our while loop. And then after that, we need to actually add in some conditions to go through and see essentially what we're looking for, like as far as our maximum profit. Okay, so I think that instead of having it be a normal while left is less than right, I think that we're just going to do while the okay. I set this up as a normal 2-pointers problem, but I think that this would make a lot more sense as a sliding window problem, which we talked about briefly conceptually at the end of our last session, but we didn't actually implement. So in a sliding window problem, instead of having your 2-pointers start at the beginning and end of your list, what you're going to have is you're going to have 2 pointers that are essentially segmenting your list into a smaller list. So in this case, you might have a segment that would be just these 2 or 3. So our 2 pointers are going to be set to index 0 and 1 from the get-go, which means that our while loop needs to look a little bit different in order for this to be executing properly. So instead of it being while left is less than right, because in this case, they're going to be right next to each other. So like that would just be a slightly more efficient version of a while loop, or more efficient version of a for loop. And the whole reason that we're doing the sliding window or 2-pointers problem is to make a more efficient version of solving this problem. So what we're going to have is while right is less than the length of our list of prices. So what this is essentially checking for is to see while our bigger pointer is less than the length. So we're not running longer than our list, but we're still making sure that we see everything in our list. So while our right pointer is less than the length of prices, we're going to go through and find our profit as well as the max profit. But we also, what we want to find is essentially that our left pointer is less than our right pointer, because like we had said earlier, we want to make sure that we're buying at the lowest possible price and selling at the highest possible price. So we want to make sure that our left pointer is lower than our right pointer. So we're going to have another if statement in here to check that. I'm going to shift all of this down. I got a little bit ahead of myself. So check if value, we'll just have it be somewhat pseudocode. Prices at left is less than prices at right. This is somewhat similar to a normal two-pointer solution, but it'll be like in an if statement instead of the while loop, because the while loop needs to be slightly different for the sliding window problem. And then this will be double indented for this. So we're going to have both our profit and the maximum profit being done while our right value is greater than our left value. And if that's not the case, if our right value and our left value are equal, or the right value is less than the left value, we want to set our left value equal to the right, so that we know that in that case we just need to increment our buy price up to the lower of the two, and then we'll increment our right pointer up, because we want to make sure that our sell day is after our buy day. You can't be selling a stock before you even purchase it. That's not how the stock market works. So we'll have our else statement right here. It'll be else. We're going to set our left pointer equal to our right pointer. And then we want to make sure that we're incrementing our right pointer up regardless. Like I kind of mentioned this earlier. I think I maybe explained it as though the right pointer needed to be inside of, or the right pointer incrementation needed to be in this else statement as well. We just need it to be inside of the while loop, because we want our right pointer, aka the sell date, to keep incrementing up until we discover that we can have a bigger profit margin. So we'll have our right pointer being incremented up right here. And then we also need to have somewhere where we're actually going to return the maximum profit. So we're going to return that outside of our while statement. So we'll return max profit. And we also need to make sure that we're declaring our max profit up here. We need to set it to 0 just because of this. If we cannot achieve any profit, the default is 0. And of course, if we have anything greater than that, then it'll override it. But if everything that we see is a loss, it'll just return 0, because if we're seeing a loss, it'll be a negative number, and max number of 0 will be larger than that. All right, so this is very much pseudocoded out, but I'm going to write this out in actual code so we can kind of see how it looks and then start actually testing it. Okay, so we'll have our left pointer be equal to 0, our right pointer be equal to 1. This is a sliding window problem. And this is a interesting sliding window problem, because the window will get larger as our profit potentially gets larger, but then we'll go back down to just a 2-segment window once we see that there is no profit to be made. And then we'll have our max profit will be equal to 0. And then while our right value is less than length of prices, we will start. We're going to check to see if prices at L is less than prices at R. And if this is the case, then our profit will be equal to, I'm just going to put this down here. We'll have subtracting, and then we'll set our max profit equal to the maximum of max profit and profit. And then we'll have our else statement where we'll set left just equal to right, and then we're going to increment up right every single time. And we want to return the maximum profit. Okay, let's test this out and see what's going on. Wrong answer. Oh no. Okay, let's see what we're doing here. We're returning 0. Okay, so our max output. Okay, so it's being set globally, and when we change it here inside of our while loop, it's not updating it. So we need to change that to see, so we can actually see this change occurring at a global level. Okay. Wait, okay. I think I see what I'm also doing here. That it might be that the maximum profit is not being assigned globally, but another thing I just looked at when I was looking a little bit closer at the code is that I am subtracting the buy price from the sell price, which is not how you calculate profit. That was my mistake. I was just spitballing a little bit too quickly. I think that, I know that in order to calculate a profit, you subtract your buy price from your sell price. So we need to flip that order. Let's try running this again and see if that's what the difference is. Still no dice. Okay. Maybe it is the global issue. Okay, let me look at this code a little bit more. Okay. Huh. I'm just going to print the max profit here to see if it's actually assigning it and see what's going on here. Okay. No. Okay. So something's up with profit. So I'm going to print profit here. So in this case, what we have this, okay, it would be 0 for this. So, but this is not less than, so it would just assign it to here, and then our right pointer would go up, so it'd be 1, 5 the first time this executes. And then we should be getting here 4 for our profit, but we're getting 0. Yeah, okay. So, Let's print out that profit and see what's going on. Okay, so our profit is working correctly. I don't know why it's not calculating the proper maximum then. Okay, so we have 0, 4. This should be reassigning to be 4, 2. Okay. Interesting. Wow. Right is left and left. Prices. Prices left is less than right. Prices at R. Max profit is profit. Okay. This is in line here. The else statement. Okay. Huh. Okay. Let me see what I did in preparation for today and how that varies. Okay. We have 0, 1. 0, 1. Max profit is 0. The only thing that's different between these two is I spelled out right in this solution. I'm gonna try that, but that shouldn't make a difference. That's interesting. Check the spelling is what one of y'all says. Did I make a typo? That's what's meant. I did make a typo. And I did not spot that. Thank you. Shout out to Pineapple Farms. I spelled it as Max Profit, no I, Max Profit. Yeah, okay. Thank you for that. That was a silly error. It's always the silly ones. Okay. It looks like it's passing the test case, at least the initial 2. And then let's see if it passes. Yep, passes all 212 of them just because of a simple I. So always the silly errors. Okay, so it looks like this solution beats 32% of other solutions for runtime and a little under half for memory. So I'd say it's an okay solution. I wouldn't say this is necessarily brute force. We could eventually do better, but we have other problems to solve. So good job, y'all. Shout out again for finding my spelling error. I probably would have taken another 10 minutes trying to figure that out. Brain has a funny way of just ignoring small characters when you're coding and you've been looking at it for too long. But nice job, y'all. Before we get into our next problem, binary search, I'm actually talk through what binary search is as an algorithm. And I'm also going to talk through what time and space complexity are. We might skip over search a 2D matrix in order to work with linked list a little bit. Reversing a linked list is a pretty basic problem, but one that comes up I wouldn't say very often in interviews, but it's like a simple one that I feel like gives you a little bit more exposure to a new topic. And I'll make sure that we cover a little bit more breadth in this course with about an hour left together. Okay, but here is what binary search is. So binary search is another list algorithm, and it cuts the time complexity of searching in half by using both 2 pointers like we had previously done. So this algorithm builds on the 2 pointer algorithm, but instead of just having 2 pointers and like incrementing and comparing those actual values, in addition to that, we have a middle value where we take the start and end pointer, but we're also taking the middle value. So this is taken by finding the average of a start and end pointer. So somewhat similarly to our sliding window solution last time, where the one we just did. Let me, I guess, kind of talk through this. Similar to like how we had the profit here, we will be doing a little bit of extra calculation to find the type of profit, to find an average. So instead of just subtracting those two, we'll also be dividing by 2 to find the average, to find our middle value. But instead of it being a profit, will be like the actual index. And we're going to compare what we're looking for in our problem to the middle value instead of either our left or our right pointer. And the basic condition for a binary search algorithm is that if what we're looking for in our specific problem is greater than the current middle, then the start pointer, aka pointer 1, needs to be moved up to the middle pointer, because if what we're looking for is greater than the middle pointer, there's no point in searching between the start pointer and the middle pointer. This does assume in binary search that the numbers in the list are in increasing order. This would not work on an array that has values in like non-increasing or non-sorted order. And conversely, if what we're looking for in our problem needs to be less than the middle value, then the end pointer is set to, instead of the current pointer, it should say the middle. My apologies for that, but that's because if that's the case, then we don't need to be searching from the middle pointer to the end pointer if what we're looking for needs to be less than the middle pointer. Does that make sense, y'all? I have this diagram from Geeks for Geeks up on the screen as well to kind of give you a visual. So as you can see, we're starting out with this sorted list. We have our first pointer at index 0, high pointer here at index 9. The middle of that is going to be index 4. And we get our middle value, which is 2. And this kind of continues. I guess what we're looking for is 7 in this example picture. So we know that in this case, 7 is larger than the middle. So our left pointer becomes this. And we can go to our middle pointer and see that it's still on 7 and be increasing from there. All right. And also, kind of as a quick addition, I want to give a little dive into time and space complexity. This is something that you'll be asked in technical interviews if you're looking to find a new engineering job or just your first engineering job out of undergrad. Also, some internships will ask these data structures and algorithms questions. We'll also ask you, after you solve them, what's the time and space complexity of this problem? It's good to know the basics of these. There are many, many more outside of constant linear time complexities. There's like log of n, like double log of n. Like there's much more complex time and space complexity versions, I think it's good to know maybe the top 5 or 6. Of course, if you know more information, that's great. But just kind of knowing the basics and how to calculate that is good. So, kind of as a definition of what time complexity is, it's a measure of how many times a statement and an algorithm or solution is executed. And this is not to be confused with the run or execution time of the actual code. So the run or execution time of a code is the actual time it takes to execute the code. And the time complexity is measuring how many times a statement in an algorithm or solution is executed. And also, you do simplify your solution. So, for example, if you have multiple print hello world statements, even if all of these print hello world statements were in separate files, they would all have time complexity, like a constant time complexity of O of 1. But you don't add those together to be a time complexity of O of 2 if you have multiple. So you would just simplify it to be O of 1 if you have multiple statements in your code file that are constant time complexity. But in the case of you have hello world out here, and then also this statement of for I in names, print hello name, you would have a time complexity of technically 1 plus n or n plus 1. But because the constant isn't a part of this particular problem, and just like in general, you would round down because the n is a significant part of that time complexity. And we kind of skipped ahead here, but linear time complexity scales in tune with your input or a list or array. It'll scale linearly. And then here we have some more time complexity. So this will be for O of n to the second degree, or O of n squared. This is usually for a like 2 statements that are checking for something. So it'll be like a nested for loop and then printing out something. On this link right here, I have a way more in-depth article from Geeks for Geeks that provides you with lots of different information on different types of algorithms and what their time complexities are. Here is what we were just talking about. This is a pretty common time complexity. These are more complex. You won't run into them as much, and you won't want them to be your time complexity unless it's a very complex algorithm, just because they have bigger time complexities. If possible, you want your time complexity to be lower without it being at the expense of your code not working if you're interviewing, obviously. But also just like being able to talk about this. And if, for example, you solved a problem with a nested for loop and it had a time complexity of O of n squared, and you know that you could solve it in linear time complexity and O of n with just for I and like just like a single for loop, you can mention that when you're talking about the time and space complexity in your interview. But as that goes on, like you'll just talk about like how you would fix it in the future, essentially. If you know that you don't have the optimal solution, but you have like a more brute force or kind of like a middle of the road solution, you can just talk about that in your time complexity as well. Because most of the time during these technical interviews, they're not looking for, they're not looking for perfection. They're just looking for an engineer who can ask questions and explain their thought process, and someone they can teach, essentially. And now moving on to space complexity. The definition of this is how much memory is required by an algorithm to solve the given problem. So this is how much additional memory you're using, like including the input. Also, as kind of like an aside, this isn't as easy to confuse, in my opinion, as time and it's not like as easy to confuse like as like the total time taking that a program takes to run with the time complexity. Um, and we but I still like wanted to address this nonetheless that um, don't confuse it with auxiliary space, where the extra space used by a problem, excluding the input of a problem. Normal space complexity will include the input. Okay, so for the constant space complexity, which is just O of 1. This will be basic operations, variable assignments, linear space complexity. This will be storing elements in a list or array. This typically scales as in line with the input array. And then for O of n squared time complexity, this will be something like 2D arrays or matrices. And there is a little bit more in-depth information about different types of space complexity on that list, but I just wanted to give a brief overview before we dive into our binary search problem so that we can we can calculate these for our next few problems. Okay. We have a question. Why is the time complexity for n squared if the example is just one for loop with an if statement? Good catch. That is because I forgot to edit my slides, and as I was duplicating things, I did not put a secondary for loop. So it, I guess in this case, we'd have something like for I in names. If I I guess we could have it search through for I and restaurant names. Say, for example, we're I don't know, like a big food court, like a very bougie food court that has reservations at the different restaurants. We're both searching through the names and the reservations, and maybe the most time optimal solution that would be a time complexity of O of n. But the short answer to this is I just made a mistake when I was making my slides. My apologies for that. I should have been more clear about that when explaining the O of n squared time complexity. So yeah. Okay. So back to binary search. We're going to be solving a problem with this in just a second. I'll be back in just a minute. I need to refill my water bottle, and I'll be right back. But if you have any questions in the meantime, feel free to drop in the chat. Grab some water yourself, but I'll be right back. I'm just going to grab some water. I have my water. The green screen makes it so you can't really see it. But now we can dive into binary search. All right. Okay. So we're going to go over here and click on binary search from the questions. Also, I don't know if I addressed this earlier in today's session. Am I in Python? Yeah. Okay. So I don't know if I addressed this earlier, but all of the solutions that I'm working on, you're welcome to code them in LeetCode together with us or together with me. But I'm also going to have all the solutions in a GitHub repository with all of my notes that you can access after the stream as well. So don't stress about trying to exactly keep up if you're watching along with me. But yeah, okay. So I'm going to, I can't remember. Okay, yeah, I don't know why the search isn't there for Python, like normal Python. So we're just gonna work in Python 3 for right now. So essentially in LeetCode, the function inside the class is going to be where our solution is living. I don't know if I directly addressed that earlier, but that's why I was confused. Okay, so let me talk through the problem. So for just basic binary search, we're given an array of integers nums, which is sorting in ascending order, and a target integer. We need to write a function to search target and nums. If target exists, we can return its index. Otherwise, we return -1. We write an algorithm with O of log n runtime complexity. If we don't write an algorithm with that runtime complexity, then we will be failing the time limits of LeetCode. So we don't need to worry about that. And then we can go through and calculate our runtime after the fact. And I'm 99% sure this is just the basic runtime. This is just the time complexity of binary search as an algorithm. Because this will be, because instead of it being O of n, we're just doing a normal for loop through a list. We're cutting that time in half. 99% sure because we'll need to look at my notes, but yes, that's why it's asking for that, because it wants us to actually do binary search instead of something that's like more traditional with like a for loop. Okay, so we just talked about binary search. So what we need to do will be under here. But first, I want to talk about what we're given. I talked about this in the last session, but talking through the problem with your interviewer in a technical interview is a great strategy because it gives them insight into your thought process. And that way, if you are misinterpreting anything, then they can course correct you before you go down a rabbit hole of code that will not work or isn't doing what you're actually asking for in the problem. So just kind of like reading back your understanding the problem and what you're actually going to go ahead and proceed with doing is great. And also you can even ask a confirmation question, even if you're not confused, but just like asking to confirm X, Y, and Z is correct because it confirms that like you're on the right track. And that's something you'll need to do when you're actually engineering products as well. Okay, so for what we're given a list called nums that is in increasing order and an integer called target. And we need to write a function. We need to find target in nums and return its index. And then our edge case here is going to be if we cannot find an index for target, we're going to return -1. And our second edge case / condition is that time complexity needs to be O of log n, aka no cheating with normal loops. So just to kind of write out and give like more of an explanation of binary search, I'm going to walk through everything step by step, just like we did for our previous problems, and then we'll code out the binary search. So we need to, first of all, create 2 pointers at beginning and end of our list. We need to create a middle value. I can't remember if we do this inside of our while statement or outside of our while statement. And then we are going to have a while statement of while our left pointer is less than our right pointer. We're going to see, and then we're going to calculate our middle value. So this is going to be let's see, that'll be right minus left, and then we'll divide this by 2. And after that, we just essentially need to search with our normal if statements like we would in a typical 2-pointer. So do it like this, and then I guess no, we'll do trying to differentiate between like the normal if statements and kind of indentation. This is pseudocode, so it doesn't need to be quite sensical completely, as long as you'll get the gist. We're going to check if middle is, and it'll be nums at middle, because again, our middle value is actually a pointer / integer value or index value, and we are checking to see if our middle value is like how it compares to our target. So if it's greater than our target, we need to adjust, and we'll do that by changing our right value to be equal to middle minus 1, and we're going to be subtracting 1 from middle because we have checked here, and nums at middle is going to be if it's already greater than target, then we know it's not going to actually be middle. So we know that it won't be that, in addition to the fact that we know that we don't need to check for all the values in between middle and right. I don't know if I explained that the right way the first time for adding that additional -1 or subtracting 1 from middle when reassigning, but I wanted to emphasize that we do need to subtract and add 1 to middle instead of just assigning it to middle itself. Okay, and then we'll have check elif, and we'll just be checking for the opposite. Nums at middle is less than target. In that case, we know that we need to set our left to be equal to our middle and add 1. There's not going to be 2 7s, that'll be 8. And then finally, we'll have our else statement that is just going to be returning the indices of our middle value. So we're going to return middle otherwise, because we know that our nums at middle, if it's not greater than, and if it's not less than our target, we know that it is our target, which means that we know it exists. And then we can just return our middle value. And the last thing we need to do is have our edge case, where we return -1 if we don't find any integer for our, or any index for our desired integer. So that is binary search kind of typed out. Now let's code it out. So we'll have left, right will be the length of nums. Forgot what the name of the list was for a second. While left is less than right, we're going to go through and calculate this. I made a little mistake earlier when I was typing this out that I'm now realizing. So instead of having the difference between left and right when we're calculating our middle, we'll be adding them together because we're finding the average, not the profit. I think that by including our previous example that was similar but not quite, got the wires crossed a little bit. Happens when you're coding, happens when you're a little tired. So just wanted to make sure that I emphasized that so no one got confused when I was doing something differently. I'm going to find the average, not the profit, and then we're going to check right here. Our nums at middle is greater than our target. If that's the case, we need to update our right pointer to be middle -1, and then we'll check for the opposite. So I'm just going to copy this, make my life a little bit easier. And then we'll reassign our left value. Left plus 1. And then otherwise, we can just return middle because we found our target value. But we want to make sure that we have some edge cases. So we'll return -1. I don't think we need all this spacing. I'm going to get rid of the spacing. There's enough. Bring this down. Okay, now let's run this and see if the initial test cases pass. Awesome. The initial test cases are passing. Oh no. Huh. Okay. So we're getting -1 when it should be 0. So I think in this case, because we need to account for input list where the length of the input list is only 1, we need to have it be while left is less than or equal to right, instead of it being just less than right. That way, for cases where the list is just length of 1, then we're able to actually view all the values instead of it needing to be a longer list. Let's see if that fixes our problems. It does. Okay, awesome. So runtime is excellent. This is O of n, or O of log n, my apologies. And then our memory, not amazing. It beats about 13%. For our memory, let's see. So we have 2 constant values right here, as well as another constant value right here. I'm just going to double check on that just to make sure that I am not saying the wrong thing in my sleepy brain. Okay. Yes. Okay. Yeah. So I was correct. The space complexity of normal binary search is just going to be O of 1. We completed normal binary search, so it will be a space complexity of O of 1. So the time is going to be O of log n, and the space will be O of 1. I am slightly curious to see what beat our memory. So I'm going to click on this one. It looks like it's a popular solution or popular memory allocation. Let's see what they did differently. It looks like they essentially switched the order. So they're checking to see if it's equal before, and I guess that saves some memory. Interesting. I didn't know that changing the order would save that much memory, but I guess it makes sense because if it is equal, then you can save those 2 lines on a few occasions. But that shouldn't alter the memory all that much. But I guess you're having to change this slightly differently. I don't know. Me code can be a little strange like that sometimes. But anyways, that was a good solution. Good job, y'all. Hope that's making sense. All right, quick time check. We're a little bit under half an hour, or a little bit over half an hour left. So I think we have time to do a 2D matrices and no, I think we're just going to go with the linked list problems for now. I think we'll do both reverse linked list and linked list cycle. And then I'll leave 2D matrix for y'all to do later, or if we potentially have time towards the end. A 2D matrix, searching a 2D matrix is going to be somewhat similar to binary search, but more complex and I want to give it a little bit more breadth for the implementation. Okay. Oh, cancel. All right, let me blow my nose one more time. Apologies, I'm a little sick. Trying to get rid of that cold. Nose. Oh, I'm back. I think my audio's on now. Nose has been blown. All good to go. Okay, so for linked list, this is an entirely new data structure, which is why I wanted to give it a little bit of time so we can focus on this. Oh no, I think the sneeze coming off. But basically, a linked list stores data using nodes. And what a node has is it has both the actual value that's stored in the node, and then it has a next value. And the next value will connect it to another node that's inside of a linked list. So a linked list is essentially all of these nodes that are connected together. And the beginning of a linked list is a head. So instead of having an indices in a linked list, you have a head value. And the head value is how you navigate throughout the linked list in combination with .next. So if you're given the head, you're given this, like this node right here at 1. And if you wanted to access 2, you would write head.next.value, or .val for shorthand, as you can see here. And then you're able to actually access that too. So it's a much more complicated way of structuring data. But sometimes it makes sense, especially for like profile data, when you want it to all be linked under one profile. I'm drawing a blank for other examples that it can be used, but it is a somewhat commonly asked type of question, both reverse linked list and other linked list type questions in data structures, data structure, or just technical interviews in general. And I'm sure there's other engineering applications that I just have not run into in my career thus far. So I'm just going to kind of begin to play with this linked list before I talk through this problem, just because we haven't worked with this data structure before, and I want to make sure that y'all understand what this is going, like what's going on with this. All right. Give me just a second. I'm about to sneeze. All right, thank you for dealing with me. All right, so here we have our linked list. I just want to print out the head so y'all can kind of see what that looks like, and then print out head.value, as well as printing out head.next. So you can kind of see like what these actually look like in practice before I start talking through the problem and how to actually reverse it. I know. None type has no attribute val. This means we're running into an empty linked list. So much fun. Okay, so that's an empty linked list. I'm going to do it if. So if the linked list exists, then we'll do this. Okay, so here we are getting some actual information. So this is how the linked list looks. When it's printed out, like as the input, it looks similar to a list just for simplicity's sake, but this is what the actual data structure looks like. As you can see, you have the list of different nodes that are connected, and at each of the individual nodes, you have the value as well as the next, and inside of that is just the node kind of nested. It gets a little bit weird. Linked lists aren't my favorite, but there's something you need to know, at least for these types of questions in interviews. And then as you can see, nested inside that node, the value nested for the rest of the node, on and so forth. And then you can see here, if the head does exist, then you're going to print out the value, printing out 1, which was the value of the head at that time, and then head.next, we're printing out the next value of our head, which is list node that includes value 2, 3, 4, 5, and so on. So now that we understand linked lists, kind of, does everyone understand that? Does that make any sense? Do you kind of generally understand this data structure? I will continue going on, but if you have any questions, as always, like drop them in the chat. I want to make sure that y'all understand what's going on. Okay, so sorry. I'm going to comment this out, and then I'm going to put up here is where we're going to have our walkthrough explanation / steps. Okay, so what we're given and then what we're going to do. So now it's time to actually read through our reverse linked list problem. Given the head of a singly linked list, we're going to reverse it and return the reversed list. So here's our example. We're given a head of our linked list. So it'll be the value of 1, and it goes down here where the next value is 2, 3, 4, 5, etc. What we want to do is that we want to return it. So the head of our linked list, the same linked list, we're not making a new linked list, begins with 5. And then 5's next value is the 4 node, is the 3 node, is the 2 node, etc. As you can see here, here's a more simplistic one where it's just a 2-value linked list. We have 1 going to 2, and then we reverse it. And then in this case, there is nothing, so we're just going to return the empty node. So what we're given is a head of singly linked list. And what we're going to do is we're going to reverse the linked list, and we're going to return it after it's been reversed. And also, for those of you wondering, I don't know if this was something that stood out to any of y'all listening, but we're specifically doing this for a singly linked list. There are doubly linked lists where you have a previous value and a next value. Those are complicated. We're not going to get into them today, but that is what we're dealing with. It's just a singly linked list that has a next value to a previous value as well. So in the case of this, we're going to want to hold our current value as well as our previous value, so that we are able to manipulate the next values a little bit easier. So we're going to create 2 values right here. One to hold, sorry, got to sneeze again. Create 2 values, one for current and one for previous. All right, let me sneeze. Apologies for the cold. Okay. Cold, momentarily dealt with. Not over. And then after we've created those first two values, we need to actually loop through / iterate through our linked list. And we need to, inside of that while loop, or inside of that iteration, spoiler, it's going to be a while loop, of while we have a current value, we're going to need to manipulate the data in order to change the previous and swap around the next value, and we're going to have our previous value be holding something. Since this is a singly linked list, we're able to have that previous value be a dummy value. So we're able to hold the previous node. So kind of as an explanation of what we're going to do is we're going to have a current and a previous value. Then we're going to set our current value equal to the current head of the linked list. And we're going to set a previous to essentially hold what the previous node was as we move on. But we're going to start out with our previous node being equal to null, because when we switch our previous value, or what one is pointing to, when we flip the linked list, it's going to be pointing to null / none, as you can see the end of these linked lists are. And then we're going to, as we loop through / iterate through the list, we're going to swap the values around. And then we're going to return the initial, they're not going to return the initial value. We're going to return a previous value that holds the new head of the linked list. Okay, so now that I kind of talked through that while pointing the diagram, I don't know if my mouse was moving the way it should have. Let me talk through this a little bit more. Current will hold the head. Previous starts at null, moves to old nodes, and then we're going to iterate through linked list via while loop. And then inside that while loop, we're going to want to do a few things. So what we're going to do is we're going to have a dummy next value to hold the in like the future nodes. So we want to essentially be holding the 2 through 3 or 2 through 5 here of these nodes. We're going to be holding them in a next value, so that when we flip the next value of 1, we're not losing all of this. It's not just going out into our program, but we're actually storing that. So we're going to have a next dummy value, and we're going to set that equal to our actual next value. Now, after that we do that, what we're going to want to do is we're going to want to set the next value to our previous value. So we can kind of swap those around. And what we're going to do is we're going to set the next value of current will be equal to our previous value. So we're going to swap those around. Or gets, not swapped, replaced is a better word. And then after we replace the next value with previous, we want to change out the previous value to be equal to current, because we're moving along, because we want our previous value to be equal to the previous node. And we're going to do that by reassigning our proof value to equal our current node. And then after that, after we reassign our previous value to our current node, we need to do is move our current value up. And we're going to do that by setting it equal to our next dummy value. That's where we were holding all of our stuff. Okay. So we'll have our new current is equal to next dummy. And then after we've done that, we need to actually return our value because we've done all the swapping, but we need to actually return the new head. And the new head is going to be previous because as you can see, because we're reassigning our previous value to our current node, when we finally get to the end of our linked list, it's going to be it's going to be our actually like our new head once we have reassigned that to our previous value. Okay, so we're going to just return our pre-value outside of our while loop, and that is all we need to do for our reversal of a singly linked list. So now let's move on and actually convert this into code. So we're going to create our two values. Current will just be equal to head because that's where our current head is, and then we'll have our previous, which will be equal to null. I want to have it be none. I can't remember which one works out. Yeah, I think none is what we'll actually be looking for because this is the verbiage or syntax that is in our current node. But yeah, okay. And then we'll have while current to start our iteration through the entirety of our linked list. And why we assign this to a dummy value is that we still have our head intact. So we're doing this in line and we're still able to access the head of our linked list. Okay. And then let's see what our next step is. We're going to have our next dummy value be equal to next is going to be equal to current dot next, and this is going to be equal to this right here. And after we've done that, we're going to replace this with our previous value. So what we've done so far is we have assigned 2 through 5 to our next value right here. And then we've assigned this arrow right here to none. So we're swapping that arrow around. And then after that, what we're going to do is be reassigning our previous value to be equal to our current value so that we can move on to the next one. This is kind of continuing to iterate our value upward. Yeah. Okay. And then because then our new previous value will be our new, it'll just be iterating it upward and onto 2. So our new, our new previous will be 1, and then we'll iterate our current up by 1. Yes. My apologies. I myself get a little bit confused talking through linked list. And then we're going to set our current equal to the next, and that is what's going to actually iterate this up. So then we'll have our current equal to our artificial next value, and then here we can return our previous value. Okay, so kind of talk through this once more to make sure that this will all make sense and we're doing this in the correct order. It is simple, but we do need to complete everything in the correct order. So we have our next value being assigned artificially to this. We're assigning our current value or current.next value to the last one. And then we are assigning a new previous so we can continue to swap those arrows. And then we are moving on up. Okay, let's do some test cases. Okay, it's passing the initial test cases. Awesome. It's passing all of our test cases. So our runtime is great. And then our memory is okay. Nice. All right. Does anyone have any cracks at what the time and space complexity are for this one? I'll give you all a few seconds. Okay. So I will just walk y'all through it because we have, let's see, that's what was accepted just a minute ago. Move this over here. So our time complexity for this is going to be O of 1. It's going to be constant time complexity because we just have assigned new placeholder variables. And we're like doing a pretty basic while loop. Yeah. Okay. Yes, this is what I meant to say. I kind of swapped them. Okay, so space is O1 and the time complexity is O1. It's a while loop. Beautiful. Okay. So we've solved our reversal of a linked list. I am going to move back to our slides and go through some resources really quickly. I am getting a similar error on, or not error, I'm getting a similar notification from my computer that's similar to what I got on the first version of the stream before it just kind of decided to shut off. So I want to make sure that I get all the information to y'all before that happens. So we went through a bunch of problems. I'll upload the solutions that we went through up onto the GitHub after today's stream. And you'll be able to access those as well as these solutions to the problems we're not able to get through today. If y'all can still hear me, my screen is frozen again. Go back to our first, just a minute, and hopefully it's able to unfreeze. If I'm not able to get back on, I will upload, or not upload, I will embed the links to the slides and the GitHub, and as well as the MLH feedback link. Oh, they're slightly less frozen. Okay. My screen. Okay. Okay. Yeah. Okay. The short link. Wait, it's okay. I'm kind of back. You can access the slides at GHW. The link to the GitHub solutions in there, and a great MLH really values. I'll put the link for the feedback in the Discord because my computer is bugging out again. I can't type. My apologies. I'm not sure. It's just network issues or if I need to replace my battery. But thank you all for tuning in. If you can still hear me, really appreciate it. I'll put the last tidbits on the Discord for the solutions as well as the slides. My apologies. But thank you for tuning in. I was glad we got to get through as many problems as we did, and hopefully you were able to learn something today. All right. Bye-bye.